Thanks for coming back from the break and coffee break. It's always hard to do that. We're seeing more and more interest, by the way, in all of the workshops that we're doing on topics around Dockers and containers. And we're very happy to have Christian Kniep that will talk with us here about the usage of Linux containers. Thank you very much, Christian.
Thanks, Gilad. Thanks, Sydney, for inviting me. It's always fun to talk at HPC Advisory Council workshops. And I mean, it's amazing seats here, so I'm very happy to be here. Not only because of the seats. It's fun. So today, I would like to talk about the state of Linux containers. I think it's the third time I have this first slide here on the HPC Advisory Council. I used to work in HPC like a couple of years ago as an engineer and architect, and then I pivoted to startups in Berlin. And from next week on, I will work for Docker, so I'm kind of pivoting back to possible HPC territory again. So if you like to talk about it with me, then catch me when the break is, or I think after the workshop. I'm happy to talk about containers all over the place, so just catch me if you can. So containers in a nutshell, I just want to get a brief recap for those who are maybe new to containers or those who need a little refresher on what containers are and how to contrast them to virtual machines. In traditional virtualization on the left-hand side, we have a hypervisor that's running as a service or that's even baked into the operating system. And on top of this hypervisor, we have virtual machines. So emulated hardware at first, and these machines are totally isolated from the underlying system. From what they have in common and what they don't share, the perspective is that on the operating system underneath, they share everything, and the guests itself, they have nothing in common, they share nothing. They cannot see each other, they cannot reach out to each other, so they are not related and do not see each other. And within the virtual machine is the same as the underlying machine. They are, again, completely isolated, but they are in between themselves, they share everything. Containers are different, and they don't have a specific or a kernel in each virtual machine. They are using the same kernel that is used by the underlying system, so the kernel sees everything that's going on in different containers, and he can schedule resources like CPU, memory, and so on according to the needs of the processes within the kernel. And it doesn't, is not abstracted and obfuscated by the hypervisor layer that does the scheduling for the virtual machine. And they are separated by kernel namespaces, which I will show in another slide. And each container has its own user land. So the underlying host could be Red Hat, and each container can have a different operating system. It has to be Linux though, because it's Linux containers after all, and they share the same Linux kernel, but it could be Ubuntu, Red Hat, CentOS, and all the different Linux operating systems that you can think of. You can put it in a container. And you can even only use a limited file system that does not have systemd or does not have an init system that runs only one process. But this I will touch also in a later slide. And they share something because they share the same kernel. So, and this was is a great security fear from like 2 years ago which has some merit to it or had some merit to it. Because if you have a kernel exploit within the container, then you exploit the host kernel. So if you can be root due to a kernel exploit, then you can be root on the system. And there are a lot of syscalls you can exploit, right? There are 200 of them or 250 even. So that's why they share something, and this might be a little problem sometimes. If you elevate this and do a little mix of traditional virtualization and containerization, you can put the traditional virtualization underneath the containers so that you have a virtual machine running a container runtime, and then you can run your containers within a traditional virtualized environment, and then you have a mix of both worlds. So you have the shared nothing or shared everything underneath until the hypervisor comes in place, and then you put a virtual machine on top, and within this virtual machine you share the same kernel, and you have the luxury that if you can exploit the kernel, you are only root within the virtual machine. And news alert, that's how public container clouds operate, right? So in Elastic, in AWS or in Azure, you have virtual machines running a container runtime, and that's how they operate. From a different perspective, one could look at it from an interface view. So applications either use syscalls directly or they use userland libraries to interact with the kernel. So they have like this intermediate step to syscalls. And this userland or this syscalls, they are queried or fired against the kernel. And the kernel then orchestrates and schedules resources to use the hardware. Or in the traditional virtualization phase, you have a hypervisor that emulates the hardware for the virtual machine, and then the hypervisor itself uses syscalls to query the hardware directly, or the kernel of the underlying system, and then the hardware directly. And this is done by hypercalls, and there are a lot of things we could discuss here, but let's just put a box on it and say that's virtualization magic. There's a lot of things you can look at through here, like SRIOV, PCI pass-through, HMV, and so on. So, but this is how this is abstracted. You have a hypervisor and the underlying operating system figuring out what's the best to make the application run and work as it intends to run. On the containerization side, it's much more simpler because you just have one kernel, and then you have the hardware, and on top, you have the userland and the application itself. And this is what a container is. It's just the file system of a container of an application which is then issuing syscalls against the kernel. That's it. It's a very lightweight abstraction, and the overhead is pretty negligible because you don't have the hypervisor figuring out who is first to run something. The kernel has control over all containers. If there are 500 containers on a host, they are all just process groups for the container, for the host kernel, sorry, and the host kernel can work as if it would be just 500 processes on the host. He has to obviously take care of the namespaces, but this is not much overhead. And syscalls are plentiful. As said, I think it's 250 or 300 even. I forgot the real number or the correct number, but the syscalls are very plentiful. And all of the syscalls have to be looked at, audited security-wise to make containers completely secure. And we are on the trajectory to do so, but it's not as simple, or let's put it in quotes, what hypercalls are. Like hypercalls in Zen, we have 35 or 40 hypercalls that are especially designed to make virtualization a thing and make virtualization secure, whereas syscalls are not made up with containerization in mind. But what is containerization? So the first thing to look at is kernel namespaces. And for the kernel, as said again before, the containers are just a grouped process. And they are isolated by kernel namespaces. The simplest one is the pit namespace. So if you spin up a container, then it will have its own pit namespace. And all the processes within the container can only see the processes of this given container because they have a new pit namespace. So a simple C example, I think most of you are familiar with C. This is just a simple program that spawns a process or clones a process within a little program, which, as this little rectangle, little wrench on the bottom shows, uses a new process namespace. And if you run this one, then it will show you that the overall process, this PID program, has the PID 14,733, but within the child, it thinks that its ID PID, it's 1. So it gets a new process tree, process namespace, and within this namespace, it has the process ID 1. So that's all there is to talk about for Linux namespaces. It's pretty straightforward in a sense. And if you run a Docker container or whatever container, that's exactly what's going on here. So I do docker run -t Ubuntu, and then this ps-ef command will be forked into a new process namespace. So it shows there's only one process first for this container, and this process is pit number 1. And that's kernel namespaces. There are other namespaces, so for now there are 6, like network mount, IPC, UTC, and users, and I don't want to go into them in detail, but and there are 2 others, so C groups and RDMA, one of which, like RDMA, might become something for HPC. But let's not talk about them in detail. I think that's easy to grasp somewhere else. If you start a container, all of the namespaces by default will be created for this specific container. And but what you can do, and where this thinking or this thought experiment of, yeah, it's just a virtual machine breaks, is that you can share namespaces. So you can have two containers sharing the same network namespace, as I indicated here with this yellow rectangle in the back. But they could also share the same PID namespace so that they see each other's processes. Or they can also share the same IPC namespace so that they can do inter-process communication between each other, which is normally prohibited by the kernel namespaces. So this isolation feature can be weakened, and so that containers can work together and do a lot of cool things doing this. And the restrictions are applicable through three groups. So kernel namespaces, they don't care about who is consuming what. They just make sure that the isolation is in place. So if you run a container that consumes all the resources of the host, no one is stopping this container from doing so. It's just as if the two process groups would fight on a normal system. The kernel doesn't care about who is taking or who uses more resources than another. This can be done with C groups, which is the way C groups work for a long time, right? You can say this process tree is in a certain C group, and this C group has different scheduling parameters, so that the kernel only applies so much shares to this process tree and another part of shares to the others. And then this can limit the consumption of resources. So you can tell a container only to run or to work with 1 megabyte per second network capabilities, for instance, and then the kernel will constrain this container to 1 megabyte per second, which is pretty nifty. And the namespaces are not new. They are like for 15 years now. They are in the kernel. It's not really that something someone notices, I guess, because that's just how Linux works internally. You have namespaces for this different resources. But if you don't use kernel namespaces virtualization, then you only have one namespace for each of them, and that's your Linux operating system. If you have a virtual machine, then this virtual machine, since it has its own kernel, has its own kernel namespaces as well. And with containers, you put in a new set of kernel namespaces that are controlled by the kernel, but the kernel will create new namespaces for each of the container. But as said before, you can blend this namespaces. So you can even use all the namespaces of the host so that you are essentially running a container that looks for the kernel as if it would be a process that's running directly on the system. And just to elaborate a bit on how this works for Docker for Mac or Docker for Windows. So as my laptop here doesn't have a Linux kernel, I need to run a virtual machine to have a Linux kernel. The same goes for Windows. If you want to run Linux containers on Windows, you need to have a Linux kernel, so you need to run a virtual machine. And this is where Docker came out with Docker for Mac and Docker for Windows, which just runs a virtual machine using the native virtualization of the system. So this uses Hyper-V. Windows uses Hyper-V, and this uses Xhive, so the virtualization that is native to Mac. And then I have a client and a server, so the client runs on my Mac, the server runs in the virtual machine, and when I want to start a container, then this container, the command will be issued to the Docker daemon on the host, or on the virtual machine, and then it will run a container there. And if you, to really break the notion of containers are just virtual machines, I have a little scary experiment, so if you are easily distracted, if you're easily scared, so distract yourself for a minute. Because what you can do, and I pointed to it a couple of minutes earlier, you can run a container like a host system process. So if I use privileges, it will be a privileged process, so a root process basically on the host. Then I put off the brakes or like pull out the brakes for security. So I use a seccomp profile that is undefined or unconfined. And I use all the namespaces of the host. So the PID namespace, the UTS namespace, IPC namespace, and net namespace. And then I mount the host file system in a directory into the container. and I use a simple Alpine container here. And then I'm essentially a process directly on the host system. And as the file system of the container cannot be, like, it's not a namespace for this file system, so I have to change root into the host file system. And then I'm basically the same, I'm running identically as if I would run SSH and use it to get into the machine. And since the Docker virtual machine doesn't have SSH activated, this is how you go to the virtual machine of a Docker host on a Mac or on Windows. And then you're basically a process there. And if you're totally nifty, then you change to the Docker user, and then you're the same kind of user that's on the virtual machine. But let's get away this scary thing. So the benefits of containers is first packaging. So you package it once, and you can run it everywhere. I mean, this promise was made over the last decades, I think, a couple of times. Virtual machines were promoted the same, but now it's really there. So you package the container, and then you can run it everywhere. The distribution is very easy. You have a reproducible and easy shareable package because you have multiple file system layers, which I didn't talk about, but it's just, you can imagine it like Git, so you have multiple commits in your Git tree, and the master can be identified with a SHA hash, so you can fully identify a container with this notion here, so you have the container name, and then you do SHA, and then you put the SHA hash here. So imagine you are a bioscientist and you want to be able to reproduce what you did last year or today in 1 year, then you can just save the container in the Docker registry and identify it with this hash, and then you can be sure that next year when you want to use it again, you will run the same application. Because if this SHA hash didn't match the content, so it's content hash, if it didn't match the content, then it won't run. And by doing so, you can make very reproducible repositories of your experiments. And you can put the SHA hash in your paper, and then everyone else can reproduce what you have done, which is not that easy now, as you all know. And a simple usage, so the kernel has this for years, and Docker brought it to the masters a couple of years ago so that everyone is able to use it. And I think it's a pretty easy user experience. And monitoring and auditing is for free, and I will touch on this in a later session today. But since the kernel knows about all the processes, he can easily get metrics and logs out of it. So that's also very interesting to look at. And what no one is really talking about yet, but which we will talk about in the years to come, I think, is that you can have hand-tailored userlands. So you can have an empty file system. You put in the binaries and libraries you need for your specific workflow to run. And then you have nothing else. You do not have to care about services like slurmd or SSH or whatever. You can tweak and tinker with your userland as you please. And so today we are mostly comparing native to containerized userlands, but I think in the future we should compare the generic against the optimized userlands of the container. So you don't have to agree with every other group in your university or company to run a certain set of installations, a certain set of packages, but you can create your own userland, and then you are free to do whatever you please, and you can tweak it and optimize it, and yeah, that's pretty nifty. And I did this a couple of years ago at the China conference, 2 years ago. I made a little comparison of the MPI benchmark, and it turns out that the native system was beaten up by Ubuntu in a container by a fair margin, and it was CentOS 6, and this showed that it's easy to, or it's possible to beat the native system because it has to be generic with an optimized userland. Okay, I have a little demo. I did this stack also, I think, a couple of years ago. It's pretty simple. It has a couple of containers, like a console container, which orchestrates the whole thing. I have a Slurm control daemon container, and then I have 4 compute nodes. And when I fire this up, goes up -d, it will create the containers. Here they are running. And if I create a new process within the first compute container, which is basically, it feels like SSHing into it, but what I do is I create a new process here. So if we look at Pius -EF, then this one was just created by me. and the rest was there before. And this is the tree, right? So this is the PS command I used. And here I have now a little Slurm cluster. I have a little ring demo here, which just is a ping pong that goes around. And if I do a batch stop with it, then this should be fairly fast. It will just send 10 messages around. It will decrement it to 0, and once it's at 0, then all the other processes or all the other ranks will exit. So this is basically a little Slurm cluster in containers. They have their own namespaces. They have their own host names. They have their own, all the namespaces, but they're on the same system. So, but it looks and feels like virtual machines. And this is pretty old. I did it, like I said, 2 years ago. Okay, so I kill them later. That's a little Slurm demo. And containers for software development is a thing that's like spinning for a couple of years now. So it's easy to create production-like environments with containers because they are totally isolated and they have their own user land. So you can run Postgres, Memcache, whatever, Elasticsearch, all the things that you do not know how to install or that you do not want to install because they are so complicated. You can just spin it up in containers and then you can develop against them. And that's a really easy way to get started because you don't need the installation anymore. And it's a little bit, I think that's like, it's a little bit like Python's virtual env on steroids because you don't even, you do not need to only be reduced to the Python packages, but you can create a Docker Compose file that specifies all the development environment that you need, and then you can develop against it. So to run a container, you need a runtime. That's the name, right? So for Docker, it's runc, and runc is the project in CNCF. I think, was it CNCF? Which just creates this a little tool to run a container without running a daemon. So you do runc and then run, and then you will create a container, but it won't detach. So you can just interact. It's a very low-level runtime to create containers. It's a reference implementation of the OCI, which is the Open Container Initiative. That's a format for containers that everyone agrees on. And this is what Docker pushed forward and contributed. There's another runtime which is somehow popular. It's Rocket from CoreOS. It's similar. It uses the same techniques as runc, but it's not maybe not as widely used. But it's also a runtime to download, verify, and start app containers. They call it app containers, and they have a different specification. But it's all more or less interchangeable. And then we have Singularity, which we talked about here at this conferences a couple of times. It's a runtime that is aimed to integrate in existing and share everything workflows. So it's, I mean, maybe it's fair to say it's a wrapper around your binary, and it will do some magic with the execution so that it's contained in a container-like environment. That's maybe the 30-second gist of it. And this is share everything again. So it can use some Linux container technologies, but it doesn't need to. And then we have the share nothing approach, so you can plug this container runtimes around, and you can use different ones, so you're not tied to runc. There's one that's called runv, which creates a virtual machine for every container to run. So before you start a container, it will create a virtual machine with a kernel, very minimal kernel, and then it will instantiate a container within the virtual machine so that you have hypervisor isolation for containers, also possible. It's a little bit, not as usable, I think, because the network is not figured out completely, so connecting containers this way, it's a little bit cumbersome, but still possible. And yeah, my runtime is nothing without orchestrations, like power is nothing with control, or what was the Audi slogan back in the days. You need to orchestrate, or you need to come up with containers, or you need an API to run against to start containers at scale, right? So you need to create containers with a kind of orchestration. And the simplest one is the Docker engine, which is using containerd to instantiate containers with runc. Then with Rocket, it's kind of similar because you can plug it into the containerd implementation, and then you can use Docker engine without using the Docker runtime. And Singularity, as touched on a couple of minutes ago, is basically a wrapper around the workflows or the work loads that you run, which can be plugged into Slurm, or I think Slurm is a canonical example, but there are other workload schedulers to come to plug it just in. Because it's not really, it's the wrapper around it, and so it's designed to run in normal workflows. And to create a cluster out of multiple Docker engines, so each node that you want to run containers on needs a Docker engine, and if you want to have a cluster out of it, you need, or multiple machines, you need to run a clustering mechanism. And for Docker, this SwarmKit. For CoreOS Rocket, you can use Nomad, or you can use Kubernetes, or you can also use, as said, Dockerd and then SwarmKit to create a cluster of machines. Then Singularity integrates with your cluster management. So Slurm, I think, as said, is a canonical example. Yeah, so that's the quick run through to the runtime and the technology and the little brief introduction to orchestration and clusters. A little three-step guide to like orchestration, a little bit more elaborate, is that there is one service orchestration or data center orchestration, which is kind of, not kind of old in this realm. There's no old technology, I guess. But Mesos was created to run a distributed system kernel across multiple machines so that you don't look at your data center as a set of individual resource pools, but it creates a distributed system kernel, meaning that it allows you to allocate CPU, memory, and I/O, and that's what Mesos does. They created a little scheduler for containers, or maybe not that little, but they created a scheduler for containers called Marathon so that you can use Mesos to run or schedule containers within a Mesos cluster. And also you could think of running Swarm or Kubernetes on top of a Mesos cluster because Mesos, as said, is just a distributed system kernel to run services across. So that's the most low-level thing to use. Then we have Kubernetes, and everyone is talking about it, very popular system or very popular framework to orchestrate services at a great scale. It comes from Google's Borg, so it seems to be proven to be very scalable, and it's matured to be one of the go-to orchestrators, I think, for services, even though it's a little bit cumbersome for developers to use, right? Because Kubernetes has a complexity to itself so that you cannot run it easily on your laptop. You can use Minikube, but still, it's not as easy. Swarm, on the other hand, and now it's like it's not an advertisement, still not working for Docker yet, but it's easy for devs to run operations. So you can use the Docker compose files that I showed before to compose your little setup on your node, and then you can run a pretty nifty setup that is local to your machine or even scaled with Swarm across multiple machines. So I think, and that's what I hear from my colleagues that I introduced this to. They said, yeah, it's easy to use and they like it. But one of the issues maybe with the Swarm ecosystem, it's very fast pivoting, so they introduce new features and then they have to start with a limited set of things you can do with it. So you cannot run a privileged container, for instance, in a Swarm service cluster. That's, to my knowledge, or that's my point of view, it's because it makes the overall orchestration easier, so they try to keep the building blocks simple to be able to do cool things with it. Whereas others try to make the building blocks as generalized for everyone to use as possible, and then they put a lot of features in it, and then it's not as easy to operate. So that's my take on why Swarm keeps it a little bit simpler, which I like, but others go to Kubernetes. Then we have status quo friendly workload orchestration, and I talked about Singularity again. This is already, that's on the bullet 2. Then there's one other from Cray or NERSC. It's Shifter, which is the first attempt, I think, fair to say, for container orchestration. They extract the Docker image or the file system out of a Docker image, put it on a distributed file system, and then you can run change root basically to use it in your cluster. And it's highly integrated with Cray systems, so if you run a Cray, you might want to look at this. And Singularity, I already talked about it. It's wrapper, it starts from the user's privilege level and it does not need to be root. And why it needs to be root is because it skips messing around with C groups, which all the other runtimes do. And for messing up with C groups, you need root privileges. So that's why Singularity has a nice shot there. And separating the concerns here, I think where Docker and Linux containers in general thrive in the non-distributed or non-HPC ecosystem is that it's easy to reproduce your work, it's easy to collaborate because you can put the Docker files in a repository and your Docker Compose files in a repository and share your work and make it work for everyone. But this is for the easy use case is just on one single machine. And you can have nifty machines like with 144 cores at Amazon, for instance, which is a pretty beefy machine. But if you want to run a more distributed workload, then you need to go to like HPC systems, right? Or you can go to the cloud. But on HPC systems, you have this limitation that no administrator wants to run a daemon that needs root privileges and then does not want to trust so much the user as to say, okay, he can do with his privileges what he wants, but we don't want to provide him most likely an API there where he can gain root privileges and maybe exploit our kernel. So that's where the complexity comes in for HPC systems, but also on share nothing infrastructures such as like AWS and OpenStack and so on. That's trickier, and this is where we struggle, or I struggle, for a couple of years now to come up with a good idea, or I have a couple of ideas, but I didn't have time, so now maybe I have hopefully a little bit more time to explore those and then present it to you. But as I showed, you can run a Slurm cluster in containers, but it has its limitations. And you can run Swarm or Kubernetes to run your services in. And I think this is what should be explored first. And then you have CoreOS, Singularity, Slurm, so on. But for running containers on these systems, like native containers, not in virtual machines or something else, that's a little bit trickier. And I think also that HPC development or HPC systems are kind of a different beast, because what you normally do in software development is you iterate on your software, right? You create new features, you put it in the code, and then you run your test. Using containers is very easy, and that's the very established workflow and was before containers already. But for HPC, maybe that's not the iteration focus. So it's not iterating on code, it's rather iterating on job settings or iterating on input data. So the iteration is a different one, and hence this is why I think containers and Docker and Kubernetes do not really have a foot in the door currently, because what you want to iterate on is different than what you want to iterate on software development. And the focus of the different pieces, I think Docker was used or was focused on beefing up the development and enabling them to do a little bit ops. Kubernetes was more on the ops side and wants to improve the operations at scale and doesn't care much about, or maybe as much about, the developer's experience. Swarm targets both, so DevOps, and I mix the terms a little bit. Maybe it's my German concatenation skill there. And yeah, Slurm scales at big clusters, right? And with Singularity, maybe they come together and make it easy for users to run container-like jobs in a big cluster. But I think there's something that should be explored a little bit more so that we can get to the right top with native containers. Look ahead real quick how I'm in time. I think I have like 10 minutes or so left, maybe, hopefully. Yeah, no? I'm done? I will just continue until Gillian, you shout at me, right? So containers are no magic, as I showed. What I did before was just a little Slurm partition on my MacBook, and if I want to run a different userland, so this one was Fedora 20, if I want to run Fedora 22 or Red Hat or whatever as a different set of compute nodes, then I need to come up with new containers. This is what I really hate about this solution, right? I don't want to spin up containers and then create a partition and then run a job that's using this specific partition, because I have to know beforehand what I need to run Slurm jobs. What I rather would like to have, and this is where the orchestration part kicks in, is that I have a Slurm cluster, and then the Slurm daemon spins up containers to run the job in. that would be my dream, and I think that's not far off. And I will work on making this happen, so that you can run Slurm, a Slurm job that spins up maybe Fedora 20 jobs from back in the days because you need to rerun something. And then you spin up a different job that uses CentOS 7.4, for instance, or whatever, with a different userland and has a tailored userland for your workload to run it, so that you don't have to run Slurm within it. You can just tweak the userland to your application, and you don't need to care about anything else within the container. So that's the goal. Let's see how we can reach it. And so not using Slurm, you can also run MPI run, right? So you can run MPI native. And if this would become container ready, it would be also cool, so that the MPI process is not forked in a remote machine using SSH or RSH, but uses container technology. That would be also cool. Or that the Swarm runtime, so the container runtime, knows about MPI workloads and helps you with orchestrating it. So it would become more of a workload manager than a container orchestrator. But that's all to be explored. But as the days are shorter now, maybe there's more time to tinker around with it. And yeah, so ideally the container engine understands MPI. So the takeaway is, and I didn't talk about it yet, but I will talk about it after lunch, reuse the software stacks that's already out there that I will talk about in a little 15 minutes talk after lunch. So that's to come. But for this part that I presented now, explore native containers for HPC. If you have time at your hand or some research that you want to do, it's fun. You can run system containers, which are almost like a VM, which I did with this virtual machine setup, which is container setup on Slurm. And there are a couple of proofs of concepts that I did with containerd to create a very simple workload manager or beef up Slurm or maybe make MPI container. Okay, that would be my take. If you have questions, you can do it now, but maybe time doesn't allow us, so you can ask me during the lunch break. And if you want to, oh no, I have a how you can contact me slide in the next presentation. So, not here. So, thanks.